Hi everyone, today we're going to talk about station 3 of our lab practical. We're going to learn how to draw an elliptical orbit. So let's start with our directions page. Number 1 says, write the eccentricity code number below in your answer booklet. They gave us the code number. I'm going to go to my answer booklet right here and I'm going to write the code number 31. Next, it says on the ellipse construction page, the last page in your answer booklet. So it's saying to go to my last page in my answer booklet. So let's do that. The last page of my answer booklet looks like this. It says circle the 2 dots that correspond to the 2 dots circled in the line below. This is important because it's telling us to circle F1 and F1 on this side. So I'm going to go to my answer booklet and circle F1 and F1. The reason this is important is because on the lab practical itself, you might be asked to circle F2 or F3 depending on which student you are. Different students will circle different ones. So in this case, I'm circling F1s. Number 3 says, place the ellipse construction page on the foam board. Let's do that. Here's my foam board. I'm going to put the ellipse construction page right here. 1 second. And it then says, where am I? Insert a push pin through the center of each circled dot so that the pins are firmly in the board. So that just means that I have some push pins available to me. I'm going to put one of the pins on F1 that I circled on this side and the other F1 on this side. Depending on which ones you circled, you're going to have to put your push pins in the different areas. Next, number 4 says place the loop of string around the pins and place your pencils inside the loop and construct the ellipse. Here's my loop that I'm given. I'm going to make sure that the knotted part of my loop is on the outside. It's not touching any of these pins, and I'm just going to loop it around my pins. Next, I'm going to take my pencil and I'm going to gently stretch out this loop, and I'm going to draw a nice circle around my pins. You might not get it right the first time, but if you keep going around, you might have a good oval. And that looks good to me. So next, I'm gonna erase this part actually, so that I have my final oval. Okay. Next it says number 5, remove the pins and string loop and return them to the container. Here's my container. I'm going to take my push pin and I'm going to take my loop and put it away. Now I have an ellipse right here. Number 6 says the ellipse you constructed represents the orbit of an asteroid around the sun. We're drawing the orbit of an asteroid going around the sun. Now it says place an S above one of your circled foci to show the position of the sun. Your foci are the circles that you drew around those dots. One of them is going to be the sun. It's up to you which one you want the sun to be, but either draw an S on top of F1 on this side or draw an S on top of F1 on this side. If you circled F2, then you would draw your S on top of F2. If you circled F3, then you would draw your S on top of F3. This is showing that in our real solar system, the sun is not always in the center of the orbit. It's kind of towards the side, and the asteroid orbits the sun around in an elliptical orbit. Now that I have an S here, number 7 says, place an X on the constructed orbit where the asteroid has its greatest orbital velocity. We want to represent where the asteroid will be fastest. So the asteroid will be fastest closest to the sun, which is S. So we're going to draw the X on my orbit because the asteroid won't be outside the orbit. On my orbit right next to S where the sun is. Because of sun's gravity, the orbit will be fastest right here. So we have my S, we have my X. Do not draw more than one X, do not draw more than one S, because there's only one sun in our solar system and one asteroid on our orbit. Next, number 8 says, use a metric ruler, measure the distance between the foci of the ellipse you constructed. Let's do that. Here's my ruler. Remember, my foci are where I put my push pins and play, in this case, F1 and F2. I'm gonna measure it in centimeters. And when I measure it, I'm gonna always put my 0 where I'm starting at F1 right here. And I see that my distance from F1 here and and F1 over here is around 4.5678. 4.8. I'm gonna put that on my answer booklet. My distance between foci is 4.8. Notice that it says nearest tenth of a centimeter. If you go to your directions page, tenth of a centimeter is just one digit after the decimal point. So I should have one digit after my decimal point. Next is asking for the length of the major axis. Number 9 says, measure the length of the major axis of the ellipse you constructed and record this distance also to the nearest tenth of a centimeter. For a recap, the length of the major axis is from one side of your ellipse all the way to the other side. In this case, if I go back to my construction page, my major axis is actually from this side of my ellipse all the way to the other side of my ellipse that I drew. I'm gonna measure the distance. I'm gonna put my 0 in the first part right here, in the first dot that I drew. And I see that the length of my major axis is around 16.7 centimeters. I'm gonna go back to my answer booklet and I'm gonna write 16.7. It says nearest tenth. I know nearest tenth is one digit after the decimal, so I'm just gonna write 16.7. Lastly, number 10 asks, calculate the eccentricity of your ellipse and record it to the nearest 1,000. You can find your eccentricity equation on your reference table, and this equation will actually be given to you. I'm going to use my calculator. I know I need my distance between foci in the top, so I'm actually going to do this here for you over here. So distance between foci is on the top. That's 4.8 centimeters. And length of the major axis is on the bottom. That's 16.7 centimeters. 4.8 divided by 16.7 is 0.287. It asked me to write it to the nearest 1,000. Nearest 1,000 means 3 digits after the decimal, so I'm just going to write 3 digits after the decimal. Eccentricity never has units, so just write this number, no units. If you do have units for this, it will be wrong. So I'm just going to write 0.287. Alright, so number 11 says, now we want to record the planet name. In this case, they gave us Mars in the space provided in my answer booklet. So I'm going to go to my answer booklet. There's a space that says planet name. They say Mars, so I'm going to write Mars. You might have different planets depending on what student you are. So make sure you're reading your instructions properly. Number 12, it also says, use the solar system data table on page 15 of your reference table to find the eccentricity of the planet's orbit. Record the eccentricity to the nearest 1,000 in your answer booklet. Page 15 of my reference table looks like this. And since we're talking about Mars, Mars is right here. Mars's eccentricity can be found in this column. In this case is 0.093. This was already written in the nearest thousands, so I'm just going to write down 0.093. Remember, eccentricity does not have units. You do not have to add units. If you do, you will get points taken off. Now, it says, number 12, in the space provided in your answer booklet, write down whether the asteroid's orbit is more elliptical or less elliptical or equal to the orbit of the planet. Now, the orbit of my planet, what we're doing right now is comparing the eccentricity of orbit of my asteroid to the planet Mars. The orbit or the eccentricity of the asteroid orbit is 0.287. The eccentricity of Mars's orbit is 0.093. The bigger eccentricity will be more elliptical, meaning more oval. So if it's asking, is the asteroid's orbit more, less, or equal to the planet's orbit, I would say Mars's orbit is less elliptical than my asteroid's orbit, simply because my number is smaller. So I'm just going to write, no, it's asking, is the asteroid's orbit more or less than my planet's orbit? My asteroid's orbit will be more elliptical because it's a higher number. So I'm actually going to write more. Whichever is the higher number will be more elliptical or more oval. last but not least, it asks me to provide an explanation of how I know it's more elliptical. And the only answer I need you to say is this, and I need you to memorize this. And this will not be given to you on your lab practical. The larger the eccentricity, the more elliptical the orbit. That's all you have to say every time. So I'm gonna go ahead and write the larger the eccentricity, the more elliptical the orbit. And that's it for now. I'll see you guys later. Bye.